Hey guys, good afternoon, everybody. Hope you guys can hear me okay? Hi, my name is Trisha. Thank you, Ryan, for the introduction. So without wasting any more time, I'll get straight into it. First, talk about the basics or the fundamentals of what pressure controllers are, and then go into how they actually benefit some of the common modern day applications and how they're used out there in the industry. With that, just a little tidbit about what is a pressure controller. So I know that term kind of is self-explanatory / intuitive, but I would still like to kind of break it down a little bit. So a pressure controller, at least the term on the metrological side, refers to an instrument which can control as well as measure pressure accurately. What that means is a pressure controller essentially has two components built into one chassis. One component which is primarily responsible of measuring accurate pressure that it sees, and one portion is responsible for actually regulating and stabilizing that pressure that it's seeing and outputting a very stable flow of pressure. So, and all of that, both of these functions are essentially done inside this chassis or this equipment, utilizing the power of software to kind of drive these at tandem and display the results on a screen for the user to see. At the same time, the operation of a pressure controller is typically done with a display, either with buttons or touchscreen or what have you. And that software piece, which is driving the automation of these two individual components, is what uses the guidance from the user or the operator to drive these two portions together inside one chassis. That's what makes a pressure controller really special, because it sort of has that element of complete automation and complete intelligence built into it, and follows the operator's instructions to drive itself to a stable pressure and to be able to very accurately measure that pressure on the line to give you a very stable output, which you can trust with a high level of accuracy without having to manually do anything. So, I mean, with that definition alone, we could understand that it's a device that is meant to or created to save time on the user's part, eliminate bulky equipment that traditionally a user would have, and increase the efficiency of the process. So with that, let's kind of take a look at what typical modern day pressure controllers look like and how they do all of these functions together. So as I said, the controller is divided into two pieces, one which is the regulation component and one which is the measurement component. The regulation component controls stable pressure. It's simple as that. And how does it do that? Typical modern day controllers have valve-based technologies built inside them, or regulators built inside them, which you used to traditionally see on benches in a big bulky system. All of that technology is now condensed and controlled through circuitry inside the pressure controller itself. In Mentor controllers, this technology is often driven through solenoid valves or needle valves, which are working together and driven through a CPU or a computer sitting inside the controller to regulate and yield a stable pressure output. Why would you use a stable pressure source, or why would anybody need a stable pressure source? Typically, when we have pressure lines coming into our factories or anywhere, essentially, they are unregulated pressure supply and have peaks and valleys in that pressure output. But when we are feeding that pressure to our devices that we are checking or we are verifying, we need that pressure to be stable enough for us to capture a reading. And that's why we need something like a pressure regulation device or a pressure controller to give us that stable output. Coming on to the second piece of the pressure controller, which is a critical measurement piece. So to perform any kind of calibration, you need a reference device. You need a device that is X times better than the device you're trying to calibrate or verify. a device that you can trust for it to be accurate enough for you to calibrate your device. And that is why pressure controllers are built in, at least in modern day times, with highly accurate reference transducers, which see that pressure source and yields an output or display a reading which is highly accurate, up to several degrees of decimal, several digits after the decimal in accuracy, so that one could trust the display of the controller and use that as the reference when calibrating a device under test. So it's an exceptionally important piece when you are doing or when you're using the controller as a reference standard. And because of both of these pieces, it can be used as a standalone device to do both pressure generation as well as pressure calibration. And that is why it finds its use into many modern day applications, because of its versatility in both of those components. Here you can see in a diagram, it's a typical diagram of a Mincer pressure controller, which is very analogous to almost any controller out there, where you will have a supply pressure come in, you will connect your device under test to the measure port or the control port of the controller. If you're operating in vacuum region, you'll also have a vacuum pump connected to it. But that's pretty much it. You'll press a button, it will go to the desired pressure, display an accurate reading for you to be able to calibrate your device under test. So it really creates an efficiency and an automation like no other, especially when compared to its manual counterparts or more traditional counterparts. And that is what makes controllers one of the most versatile pieces of calibration equipment that is out there. So with that kind of background being set about what a pressure controller is and how it's divvied up into different components, let's get into kind of looking as to where these elements can take part into yielding a benefit to the customer. So in standard production environments, controllers can be used in a variety of applications. I've chosen here 3 applications which are common in a variety of different industries and are essential to the production / manufacturing / checking of those components. Some of the things that come into mind, especially when we're thinking industrial environments, is pressure sensor manufacturing or pressure transmitter manufacturing. In either of those applications, there are elements in the manufacturing chain, like end-of-the-line testing of those transducers or temperature characterization, where you need to check those transmitters / transducers for operability and functionality. And you need to do that using a highly accurate pressure calibration system. And controllers in modern day times are kind of replacing those traditional calibration systems because of their versatility. So let's we'll go into each of these applications one by one in coming slides to kind of show how they are used in either of them. So let's first talk about end-of-the-line sensor testing. Now, any kind of transmitter / pressure transducer manufacturer in any industry, automotive, aerospace, industrial, communication, whatever it may be, or process industry, you would need to do an end-of-the-line testing of every transmitter or transducer that you're producing in order to verify the performance of that transmitter or transducer and approve it for the marketplace. So typically in traditional times, how it was done was there used to be, depending on the size and the volume of manufacturing, there used to be a conveyor system wherein all these manufactured transmitters or transducers used to end up in their final verification line. And in this final verification line, there used to be a control valve bench or a valve test bench almost, or a pressure regulation bench that would have a couple of operators sitting in front of it, manually driving each pressure point and checking these transducers one at a time or transmitters one at a time at each of those pressures. And this cycle looks different based on each manufacturing world. They could be doing 3-point checking, they could be doing 5-point checking. But you can imagine that this process was extremely laborious, extremely time consuming, and it used to be one of the bottlenecks in the manufacturing chain because of the singular nature of this testing. Now, and all of this bulky equipment combined, then there used to be a manual entry where the operator used to check these readings manually. So there was another source of parallax error or the user error that got introduced, and there was a higher risk of false positive. Now, when you compare this traditional method of end-of-the-line testing to a relatively significantly automated way of doing it, imagine you have several transducers or transmitters of the same range come into the end-of-the-line process together. There is a manifold that would mount these transmitters together. There's a communication panel built in, and there's a pressure controller sitting there, which is driving the entire characterization or entire test cycle automatically through a sequence built inside these controllers. So all the user needs to do is mount these transmitters together on the manifold and press play or press start on the screen of the pressure controller. And the controller will then automatically drive the pressure from whichever points, 3 points, 5 point, 11 point, whatever testing requirements are there in the manufacturing, automatically collect the output or record its reference transducer's reading and convey that to the communication software. The communication software will automatically grab the readings from each of these devices and could yield any kind of failures and pass testing in one go. This would save time. It would reduce the sources of error that could get introduced through the manual entry. It is fully automated, so the process is significantly more efficient, and there is a biggest bottleneck that was there that was reduced throughput is solved through this process. So we have commensurately have seen significant improvements in our customers' throughput and our customers' output and reliability of these sensors by using controllers or by using automated systems as opposed to a manual end-of-the-line checking process that they were using before. So they've seen a lot of success where controllers play a really critical role in transducer manufacturing in this stage. Another interesting area, which is, in my opinion, one of the most critical processes in manufacturing of any sensor, any transducer, any transmitter, when you go look at the data sheet of any pressure transmitter or transducer, what have you, or pressure sensor, you would see a specification over there about their accuracy or performance that is listed across a temperature range. Now, that temperature range is determined through a characterization process, which kind of correlates what the output of the pressure of that device would be in a certain range of temperature or with increasing or decreasing temperature. As we all know from the basic laws of physics, pressure is linearly related to temperature. So it is important in these manufacturing processes to record what the pressure output changes would be when the temperature is increased or decreased or what have you. And so in order to perform temperature characterization, which is considered by many people the most critical process of the manufacturing, there are huge bulky ovens that sort of almost cook these sensors at different or varying temperatures. And then there is almost a pressure regulation / observation bench system that is created, which runs a lot of pressure lines, a lot of pressure regulation systems, big compressors, big supply sources, and a lot of operating knobs to maneuver the different levels of pressure and monitor them. Now, you can imagine if this oven hosts 50 transducers, that is, you would need a pressure panel to monitor all of those 50 transducers, what different pressure ranges they're at, to drive them to a certain pressure range, observe their outputs, note the failure rate, monitor constantly the curve. This is such a huge manual entry process. It used to also be the process that used to induce a lot of failures because at any point, if there is a failure and you're recording it and you're missing the reading out of the other sensors, you're essentially having to do that process over and over again. So what happened was, and not to mention the employee requirements or the resource requirements needing on part of those manufacturers to do this process. So again, this here over here is an example of automating that process. So inducing pressure controllers or pressure automated systems next to that ovens installed in a rack-based or installation with multiple controllers talking to each other with wide variety of ranges, because modern day controllers have multiple transducers built into them. So what that means is one controller can cater to a variety of ranges of DUTs installed inside these ovens. So with controllers built next to these panels, the portion about driving different pressures to a certain set point was automated. Recording those readings was automated. Recording the reference values that they need to be was automated. So it required significantly less effort from the part of the user. And it also reduces the requirement of constantly monitoring each oven run with an operator, because you don't need to do that, because again, it's plug and play. So the process is entirely automated, and we use this process in our own facility when we're manufacturing transducers that maybe Richard will get into a little bit. But almost every pressure transducer manufacturer essentially can take their oven characterization process and reduce it tenfold in time as well as resource requirements with the use of automated devices like controllers. I've been talking a lot about how manufacturing is affected directly with pressure controller use, but at the end of the day, you would think that, oh, these are calibration devices, so what about actual calibration processes? Well, calibration processes are not just restricted to the production environment or the manufacturing facility on the sensor side. They're also, it also plays a key role on the assembly side of things or on the maintenance side of things. This is a site that is pretty common in automotive sensor manufacturing or automotive test cells or automotive system manufacturing. So you have these plethora of sensors that are installed in all our vehicles or all automotives. I mean, what have you, tire pressure, airbags, transmission, every portion of the modern day car has one or the other sensor installed into it. And tons of those sensors utilize pressure as their fundamental for measurement. So what in automotive manufacturing facilities, what they do is they build what they call automotive test stands, wherein they will install a pressure controller to kind of speak with each of these sensors of different ranges so that they don't have to have different reference standards and different pressure sources for each of these sensors. Instead, they will utilize one or two or however many they need pressure controllers, which have multiple reference standards inside it to reduce the real estate required to build these automotive test cells and to reduce the automation requirements or the communication requirements. Because imagine having a computer system to communicate with one controller versus needing to speak with multiple systems or subsystems of pressure standards. So what it does is it allows for, once this controller is built into an automotive test stand, it basically allows for both testing as well as calibration to be done in one environment alone and not having to send these separately to a cal lab or to a separate entity to get them calibrated. So you automated the manufacturing, you automated the verification, and you also performed the calibration process right in that one very step. So it really, really reduces the amount of time it takes for any of these processes to get completed. Rather interestingly, almost all pressure controllers in the market today, especially Menstrie controllers, are have built-in features like leak testing. Now, this directly associates to the first part of the presentation where I spoke about pressure controllers being used to or being treated as stable pressure sources. Now, if they are treated as stable pressure sources, you can easily check for leaks using these stable pressure sources and the transducer that is inside in a variety of applications. Leak testing is critical when you're making sealings, when you're making pressure safety devices. It is extremely critical in the packaging industry for food processing. It is also extremely critical when you're making pharmaceuticals or medicine production, because all of the packaging industry requires pressure sealing, and this leak testing of the final process is often conducted using controllers being acted as stable sources, and then leak and the delta being measured. One of the more interesting applications or out of the world applications would be space travel, wherein it's extremely important to test the leaks in space suits and a variety of different sensors to make sure that the pressure is stably maintained inside the suit. So this is a screenshot from one of the Mentor controllers, but you will notice something very similar or similar as in different types of controllers. So we have leak testing as a separate application where you can enter what your leak testing criteria is. How much delta are you allowing? What is the set point at which you are trying to measure the leak? And a very critical, which differs from application to application, what are the different types of leak rates you allow? Because often a certain application may require a very steady flow of pressure or a steady leak rate, while others may have a requirement where they're only mandating checks when there is a very severe leak. So either of those things are easily maneuverable using a pressure controller, because you can program how you want to regulate the pressure inside the controller. And based on that, how you will be able to determine how do you want to measure your leak. So in Mentor controllers, it's a separate application altogether for easy access, and it gives a very clear indication of pass and fail. But you can also do this externally using programs that talk to the controller. Again, as I said, leak testing is only one of the applications that you could do with the controller. Another auxiliary interesting application is safety testing. We've all come across pressure seals, pressure burst discs, or valve tests where sensitive equipment is tested for pressure ratings, or there's a lot of rupture disc manufacturing that uses pressure controllers to check the pressure rating of those rupture discs. And you can do burst testing or essentially safety testing using a controller by having or by driving the pressure and monitoring at which rate or at which point do you determine that there is a burst. So you can measure the delta or the change in pressure in a controller or on a device which is connected to a controller by the rate of flow of the pressure, which is exactly the control component of a pressure controller. So just because initially a pressure controller is perceived as a device for stable pressure source or a device for stable measurements, it can be used in a plethora of different ways wherever you need to monitor rate of change of pressure, wherever you need to monitor any significant drop or any significant gain in pressure because of the functionality of accurate measurement. So we talked about leak testing, we talked about burst testing, which are sort of more uncommon uses or not so prevalent uses of a controller, but they are gaining in popularity quite a bit. So just to conclude all of those different 3-4 types of applications that I ran along, controllers can be used in a plethora of applications, from automation to yields automation, which is their primary agenda, to reduce the amount of resource requirements, to have a one-box solution to a highly accurate measurement as well as highly stable pressure, to be able to eliminate a lot of secondary devices that you may be using currently and replace all of that through single device, and to be able to reduce any external sources of error that you may have due to manual entry, ill communication, differential pressures based off of open loop communication. All of that can be solved by a one-box solution like a pressure controller. Not to mention, long-term, reducing all of that footprint will yield a lot of savings. This is just showing the Menser lineup of controllers, which goes from as low as 10 inches of water or 0.36 psi, right up to 23,000 psi. They come in a variety of pneumatic as well as hydraulic combinations, and a lot of different sensor combinations within them, wherein they have dual channel or single channel functionality. So that's pretty much what I have on the controller side of things. Again, if you have any questions or if you want to ask about a specific application that you have, please feel free to ask that at the end of the presentation, or type that out in the chat box and I'll be happy to answer it. With that, I'll hand it over to Richard, who is going to talk about the sensors and the sensing elements that go in tandem with the pressure controller.
Greetings, everyone. Thank you for joining us today. My name is Richard Harper, and I am the Sensors Application Specialist over at Menser. And this period of instruction is going to be focused on our pressure sensors. And what I'm going to do is I'm going to essentially illustrate why accuracy is important whenever you're considering the purchase of a pressure sensor. So a pressure sensor is a device that receives a pressure input and produces an electronic output that is proportional to the pressure applied to the sensor. These devices are also identified by other names such as a pressure transducer or pressure indicating transmitter. And over there on the right, that's an example of one that we actually produce over at Menser. It's, it just kind of looks like a small stainless steel cylinder. On one end, you've got electronic connections, and on the other end, you have a pressure connection. I'm sure many of y'all have already seen these products before. But there's a lot of different companies out there and several different industries that all utilize this type of technology. And for the most part, they come in 3 different configurations. You can have an absolute, a gauge, or a bidirectional instrument. Now, an absolute pressure sensor provides pressure indication that is relative to a perfect vacuum. Now, this instrument would typically show something equivalent to like a 1,000 HPAs or 1 bar or 29.92 inches of mercury at sea level or inches of water. And that is just whenever you're exposing barometric pressure to the actual pressure port on it. Now, something that's a little bit different than that is a gauge instrument. Now, a gauge instrument, whenever you have barometric pressure exposed to the pressure port on it, it's going to show around 0 psi. Now, the reason for that is because you're actually going to be using something called a gauge reference. And at Menser, we produce some sensors that use a true gauge reference, which is the little hose barb that's right up there on the top of that guy. And what that does is it allows for barometric pressure to be exposed to the opposite side of the semiconductor that's inside there, actually giving us a pressure indication. So the other type of instrument that we have is a bidirectional pressure sensor. And what it does is it gives you an absolute pressure indication that is relative to the pressure that's exposed to your reference port. So it'll give you essentially an absolute reading that is how many psi or whatever pressure away from the pressure that's exposed to that reference port. So it gets a little bit hairy, and it's always good to have people to talk to like me. If anybody has any questions about sensors that we produce over at Menser, all you got to do is give me a shout, and we can try to get you to select the best one. Now, in the grand scheme of things, the word accuracy gets thrown around quite a bit. There are many different definitions for accuracy, but the main point is to remember that accuracy is how close the measurement is to the true value. Now, at Menser, we define accuracy as the total uncertainty of an instrument. The total uncertainty is broken down into linearity, hysteresis, repeatability, temperature effects, and the uncertainty of the calibration standard used to calibrate that instrument. These values are important because they're all quantifiable and allows us at Menser to be able to maintain uniformity and traceability of all the different instrument calibrations. Now, this value is typically shown as a percent of full scale or a percent of reading. An example would be 100 PSI transducer with 0.01% of full scale accuracy. That would give you like a 0.01 PSI total uncertainty. Now, whenever you go to actually have a pressure indication, it's important to think of this total uncertainty because it has an effect on the decisions that you make after that, okay? Now, another very important thing that you need to consider whenever selecting a pressure sensor is temperature compensation. At Mincer, we actually went a step farther and accounted for all the different effects from varying different temperatures. All these different temperature effects, they tend to influence the operation of our silicon semiconductors that we use to make the pressure indication. And because it's just inherent in the operation, we know how to account for it and make a very, very accurate, stable pressure indication using it. So silicon-based piezo-resistive pressure sensors are sensitive to heat. This is something that's just nature of the beast. And this can cause resistance of the bridge circuit to change. This typically results in the accuracy of a pressure sensor to drift when exposed to different temperatures than what it was calibrated at. So at Mincer, whenever we go and we build the sensors for you, part of our characterization process takes into account all these different effects from the heat. And that's how we'll go and we'll, on all of our data sheets, we'll have these temperature ranges listed under there called compensated temperature range. And it's within that range, for example, over here on the right, where you see 0 to 50 C, it's within that range that we have all the temperature effects accounted for. Now, under some conditions, if a customer were to want us to do something a little bit wider range than that, that's fine, we can do it. We just got to know the details of what they're trying to accomplish. But we've developed our own proprietary technology that allows for us to compensate for the effects of these different operating temperatures on our sensors. And in the event that you wanted to make sure that you're maintaining all of your accuracy that we have advertised, for example, if we were advertising 0.02% of full scale or 0.02% reading, it would be present throughout this entire temperature range. Something very important to consider. Now, one example that helps to illustrate the importance of having an accurate pressure indication is the elevated storage tank. Now, in the real world, there's more to automating one of these things, but the physics are all the same, right? In the example of an elevated storage tank, a pressure indicating transmitter is used to measure how much water is available in the storage tank. The pressure indicating transmitter is used to measure water pressure at the bottom, thus allowing user to deduce the height of the water column above the instrument. So say, for example, if you have a 100-foot tall tank and if it was elevated 100 feet and it was 40 foot tall, and the total height would be about 140 foot. Full storage tank like this to produce pressure reading, somewhere in the neighborhood of 60.69 PSI. It's down at the bottom there. And if it were empty, it would be somewhere in the neighborhood of 43.35. That would just be the 100-foot water column pushing down on it. Now, with an instrument that has an accuracy of 0.5% of full scale at 70 PSI, that gives you a plus or minus 0.35 PSI over the entire range of the instrument. With a 40-foot diameter water tank, that equates to about a 0.8 foot of air height in that water column. And if you go and you do the math, you can actually deduce how many gallons of water that you're not capable of accounting for because of the accuracy of that instrument. Now, out there in the real world, in reality, 0.5%, there's a lot of folks that will go and advertise that as being an accurate or precise instrument. Now, that is more common amongst, regular industrial controls and things of that nature. But at Mincer, since our background has been primarily focused in metrology, we've taken a step back and took our technology that we have produced and developed over the years and have incorporated that into process instruments that you might use in an industrial application. So if we were to take one of our instruments and substitute it in that exact same application, the physics stay the same, but the math changes, okay? So say, for example, if you have an instrument that has a 0.008% full scale accuracy at, in a 70 PSI range, that is not very much. I'm showing 0056 PSI right there over the entire range of the instrument. Now with a 40-foot diameter tank, that's 0.0129 feet of air height in the water column. All right, that leads you to deduce approximately 121 gallons of water in the air volume. That is insignificant in comparison to the air volume using the previous instrument, okay? Now, let's step back over to reality. Is it realistic to say, hey, we're gonna put one of these premium metrology grade instruments on an elevated storage tank? Most likely not, because there's more redundancy in the automation of a system like that. You wouldn't really need a premium instrument like this. However, let's change it from water. Let's say it's benzene and you're working at a refinery, and it's extremely important to know how much of a product you have inside of a storage tank. Well, the implications of having an accurate instrument are much greater, you know, if it's something other than water. You know, if it was a caustic chemical or something you had to maintain accountability of, then it's very important to make sure that you have really good accuracy and reliability in your instrument readings. But other than that, you know, our instruments are essentially a product of years and years of development of metrology assets, and we've essentially incorporated that into a regular industrial process instrument. So if there's anybody who has any questions, I would love to hear them.
Thanks so much, Richard, and also thanks, Trisha. Yeah, I'm going to open up for Q&A now, and feel free to use the chat box. I see some hands going up. Just go ahead and enter your questions in the chat box or the Q&A module in the webinar, and we will answer them as they come in. The first one here says, your data sheet mentions IntelliScale. What is that?
So IntelliScale is a method that we have developed at Minster, and it's a method that is used to essentially define the accuracy of some of our premium instruments. Now, we have a really good YouTube channel that goes in detail and describing all this stuff. And if you go and you check it out on YouTube, just go and search Minster, and there'll be about a dozen or so different videos on there. And one of those videos has to do with the IntelliScale accuracy. And it shows you the breakdown of how we go and we advertise the percent of reading versus percent of full scale accuracies. And if we have an instrument that is advertised as having something like IS 50, that means IntelliScale 50%. That means that throughout the full scale of the instrument, at the 50% mark of that entire scale is where it breaks down from percent of reading to percent of full scale, okay? And that's what, essentially in a nutshell, that's what IntelliScale is for us.
Very good, thank you. Question here says, what factors do you take into account when selecting a pressure controller? Trisha, you want to take that?
All right. Basically, choosing a pressure controller can be a complex decision, but I would say the top factors playing into a role in choosing the controller would be, first up, what is the accuracy of the devices that you're trying to calibrate using the controller? Always follow the 4:1 rule when in doubt. Although it's not a steadfast rule, so basically, the accuracy of the device under tests is of most importance than the pressure range up to which you want to do the calibrations. And I would also say, interestingly enough, the number of calibrations you're doing, especially the number of simultaneous calibrations you're doing, because it may benefit you to choose a double channel controller, which can do 2 simultaneous calibrations compared to a single channel. Also, interestingly enough, if you have a mixture of absolute and gauge device under test, different pressure types, it's advised to use, say, a dual channel controller as opposed to a single one, because then you can perform both absolute and gauge at the same time using different channels without having to be confused with which one's which. So, as I said, accuracy of the device, pressure range of the up to which you want to calibrate. Pneumatic, hydraulic would be another consideration, of course, and then a dual or single channel.
Okay, and perhaps you just answered this, but this one is a little bit more specific. What is the difference between the 6050 and the 4000?
Yeah, I mean, so I guess you said it exactly right. The difference is sort of combined into the first question. So 6050 is what I would call a bigger brother to the CPC 4000. So CPC 4000 is a single channel 0.02% accuracy controller. It can have both percentage of reading or percentage of full scale, specifically IntelliScale accuracy. And it has only one channel. So it's simple, significantly lighter weight, but performs pretty much all the other functions just like the 6050. 6050, on the other hand, has the capability of, it's almost like having two CPC 4000 side by side together. And essentially can do two simultaneous calibrations together, and has two regulators as opposed to one regulator inside the CPC 4000. It's also twice better in accuracy. It has 0.01% accuracy compared to the 4000, which is 0.02%.
Very good. Another question here. How do you do a humidity compensation in a gas pressure measurement?
Richard, do you want to take that?
Yeah, so I can share a little bit with you. So, for example, in a lot of our instruments, if you go and you look at the data sheets, we actually specify the use of pressure mediums such as nitrogen or clean dry air. It's not necessarily applicable to our industrial instruments, but definitely is on our controllers. And whenever you go and use pressure mediums such as that, then the expanding characteristics of having water vapor present within the sample pore are less significant. And if there is any type of expanding effects, then they're essentially going to be controlled by the controller at that point. Now, say for example that you're taking a pressure measurement just with one of our sensors, it's a relatively, robust instrument, and it can handle exposure to various different types of material. You're not really going to do a humidity calibration at that point, because if we're actually calibrating with it, then we're using a pressure media such as nitrogen that doesn't have any type of moisture present in the actual pressure connection itself. So with that being said, it's really not part of a calibration, but it can be part of an actual pressure indication. Does that make sense?
Very much. Thank you very much. A question for Trisha. Trisha, you mentioned burst pressure and rate of change. Is that the Menser 8000? And then there's kind of a follow on here regarding that 8000. Can it do 100 feet per minute? And there's a little bit more follow on to that. So I'm going to stop there. And if you've got enough to answer the question, go ahead, Trisha. And if we need to contact this customer afterwards, we can do that as well.
Yeah. Let me see. Can you hear me? Can you guys hear me?
Yes, ma'am.
Okay. So I think the burst pressure can be detected in either of our controllers. The specific application screen that I shared on my presentation, that was actually from CPC 6050. 6050 is only rated up to 3045 psi, whilst the 8000 goes right up until 6000 psi. So it really depends on the burst disk that you are testing and the pressure rating of that burst disk. We have seen in the past burst disks rated as high as 8,000 to 10,000 psi, and then we use our pressure controller CPC 7000. So it's really dependent on the rating of that pressure burst disk that you are trying to test. As far as the 100 feet per minute goes, I would actually have to do a little bit of math there and figure out, again, the rate really depends on the sensor that is installed in the controller, the rate at which you can detect that. So the rule of thumb that we follow is 20% of that pressure maximum transducer's pressure value is the maximum rate that we will allow. for pressure rate change. So for example, if you have 1,000 PSI sensor or inside the controller, then we will allow 20% of that, that is 200 PSI per second, as the maximum rate that the controller would safely measure or safely transit from one point to the other. Let's get together right after this presentation, get to know what the disk pressure that you are working with, and based off of that, maybe we can recommend which controller would it be, 8,000, 6050, or 7,000.
Okay, yeah, very good. I think we can handle that. A follow-up sensor question came in. Richard, what sensor do you recommend for human exhale pressure measurement?
So, say for example, you're dealing with some sort of a ventilator or something like that, or you want to measure the pressure of people breathing out. It's going to be a relatively small pressure, and we're going to need to essentially look at one of our premium instruments, which would be a CPT 9000 or a CPT 6100. And the reason why I suggest those is because they're going to give you the best accuracy at lower pressures. Okay, so it's a very different thing than trying to measure high accuracy over 1,000 PSI. We might be trying to measure high accuracy over like 10 inches of water or something. So I would look at either the CPT 9000 or our CPT 6100 for those.
Okay, very good. I'm going to give it just a couple more seconds here. It looks like we've gone through the questions pretty quickly here. One that we missed here, what materials are the pressure sensors compatible with, Richard?
Good. So if you go and you look at the data sheets for each one of our instruments, there is a section on there that identifies what the actual material compatibility is. And for example, anything that's going to be down below 5 PSI on our 6020s, they have a couple of different components inside there that are not present in the higher pressure stuff. But all the higher pressure instruments.
Yeah, but I mean, I think what Richard was trying to just discuss was that you can find a complete list of material compatibility charts in the data sheet itself. I think he was also saying something to the effect that the lower pressure stuff is more susceptible to wetted parts, let's just say, as compared to higher pressure, wherein we have a much wider range of fluorocarbon / stainless steel body on the transducer itself. So we will be able to take in different types of materials. But the modern day transducers that Mention makes is completely 316 stainless steel. So that's what essentially, in effect, increases its compatibility with a lot of different types of materials external to the sensor.
Very good. Thanks for finishing that up. A follow-up here on the controllers. Any HEISS emulation software for older PCS 400 or 8204?
Oh, that's a very good question. No, but quite honestly, sir, whoever's asked this question, I think we can work something together because I think I am quite remembering of this request, and I think PCS 400 commands are one-on-one replicated in the modern day controller, especially the CPC 6050. But we can work together if there are certain HEISS commands that are, say, not present in our user manual. You can refer to, I would suggest, 6050 user manual, which has the most detailed command sets. And if there are certain commands that you would like for us to incorporate, I am more than willing to work on that together with you. So please, by all means. But yes, definitely there is complete compatibility to the PCS 400 command set.
Okay, very good. That's I think that's a great answer, and I'll make sure to help follow up on that with you as well, Trisha. We really do greatly appreciate the Menser team for joining us, and all of our local customers and partners who are on the call today. We just greatly appreciate your business. We hope you stay safe out there, and we look forward to getting back in the field soon and working within the labs. But until then, we hope this webinar has been of value to you, and we look forward to talking to you all soon. Thanks so much, everyone.